So let's go back to Gen Chem a little bit. What needs to happen in order for reactions to occur? So if we can remember that, then you will understand and appreciate why enzymes are so cool. Because what we're comparing is a reaction that's just done in a flask versus a reaction that's done with enzymes. So we have a catalytic site. And so those are the 4 things that I want to talk about with you guys. Make sure you guys understand. Okay. So the entropy of molecules in a solution. You could envision that, hey, when you have molecules in a liquid, what are they doing? They're spinning and rotating all around. But remember, in order for a reaction to occur, the 2 species have to come and they have to align. So let's just say for this analogy, the reaction has to go, you see my fingers right there and how they can tuck into the groove of the other hand right there? Okay? That's the direction that this hypothetical reaction has to occur, is in that direction. What if it comes at this angle or this angle? It has to be this directionality. And so when you have molecules that are spinning around, what are the odds of them coming together in this path? Okay? It happens because we see reactions occurring all the time, but that takes time. It's just a probability argument. And so this experiment right here kind of demonstrates that. Okay, so when we take a look at, we have this and that. You see how they're 2 separate species? Okay? And then they come together to form one species. And when we take a look and we clock that, how fast does that have? We have a number, but we normalize the numbers and just say, hey, we have a rate of 1 for that particular example. And now the other 2, B and C, is going to look at its relative rate compared to A. So what have we done? So focus our attention. We have this piece and that piece. And what are we turning that ester and that carboxylate into? We are converting it into anyone know that functional group? Yeah, you guys got to go take Orgo all over again. What is that functional group? Acid anhydride. Okay? We have to be able to look at a protein, enzymes, catalytic sites, and know their functional groups. I'm speaking the language. So review that. Know your functional groups. So what are we doing in panel B? We're taking an ester, a carboxylate, and forming a acid anhydride. But what's the difference between panel A and panel B? We see that what has happened to the entropy from A to B? Has entropy increased or decreased? Okay, let me ask you this. What is the definition of entropy? Disorder. Motion, yeah.
Yeah, I was going to say it increased because there's 3 non-rotation.
No, it actually decreased.
Yeah.
So when you go from panel A, you have lots of entropy. Why? Because those 2 molecules are free to just move around. But then when you look at panel B, what has happened to those 2 functional groups? They're tethered together. And so yes, there's still entropy. You can never get rid of entropy, and there's a lot of entropy around those single bonds. But from free to tethered, the entropy has decreased because it's constrained. And what happens when we constrain it? Look at the rate increase. 5 orders of magnitude faster because we were taking those 2 species and getting them close to one another. Because they're tethered together, they're aligned so that they can react. And then look, if we go from panel B to panel C, what's happening to the entropy? It's decreasing even more because we know in ring structures there's no free rotation around sigma bonds, and definitely there's no free rotation around a double bond. And you can see that we even go even further, 8 orders of magnitude faster. So that experiment demonstrates the power or the power of being able to control entropy a little bit. We got to get it stop moving so you can react in the proper orientation. And this example right here was done without an enzyme. It was just done with molecules. But that's exactly what enzymes do. When it forms a covalent bond to the substrate, let's say, that first example I gave you at the beginning of class, what is it doing to the entropy when it forms a covalent bond? It says, substrate, stop moving around. You're going to just stay right here. Okay? And then we have the solvation shell. And this kind of explains what? The hydrophobic effect a little bit. Because that image right there is from what? Chapter 2. We talked about this. Why do substrates bind to its enzyme or its protein? Because of the hydrophobic effect. What's the hydrophobic effect? Can you explain that? You need to be able to explain that. And so that substrate at the left part of the graphic here, this guy right there, it's completely surrounded by water. And when it's completely surrounded by water, it can't react. It can't interact with the enzyme. Or if you have two molecules and they want to come in this way, but if they're completely solvated with solvent, the solvent's kind of like a force field that they bump into each other, but they can't actually form a bond because there's so much water in the way. So it takes a lot of energy for that water around, let's say, my right hand to be swept away. It takes energy and time. Get away, water, so I can form this bond. But that energy that we have to invest to get rid of the water is overcompensated by what? The hydrophobic effect, because those two, the substrate and the enzyme, come together, and there's a binding effect. What happens when things bind? Energy is released. So that's a stabilized effect. When we take the organized water around the molecule and sweep it away, what happens to the entropy of that water? It's organized with my hand, but when I sweep it away, it turns into bulk water. What happens to the entropy? Increase or decreased? Ordered, bulk water. It's more disordered. So entropy is increased. And when you look at the equation for Gibbs free energy, what's going to make Gibbs free energy more negative? A positive delta S. All right, go back to the Gibbs free energy equation. When entropy increases, it could, in theory, make the Gibbs free energy more negative. Any questions on the hydrophobic effect or the solvation shell? Maybe you can relate to this. Anyone in studies aviation? Like, why does it cost so much money to travel faster than sound? When you take a jet and it's going faster than sound, I don't know the exact numbers, but the cost or the fuel consumption just skyrockets. And what's going on? When the airplane's going through the air molecules have to move out of the way. And when you're going faster than the speed of sound, the air molecules don't have enough time to get out of the way. So it's kind of like hitting, I want to say a brick wall, but that's not true, right? But it's hitting mass, and that really pushes back on the airplane, so it requires more energy.
Like trying to walk through mud.
Trying to walk through mud. Okay. Okay, so this, let's see, number 3, distortion of substrates that must occur in many reactions. So what has to happen in that catalytic site? It needs to be dynamic and fluid, right? In order for that rod to break. So just be aware that things are moving in that catalytic site. It's not just the stationary, rigid structure. It's moving, or breathing, another way of saying it. And why does it have to move? Because if you want, let's say if we need our two molecules to bind like this, but they're in a catalytic site, and this hand is up here in the catalytic site, and this left hand is in a different spot in the catalytic site, is it going to react? No. So the protein itself has to be fluid and move around. And when it moves around, it's going to get to that perfect sweet spot where those two molecules can join together. Okay? So for, let's say, why does it have to start like this? Why can't it just start like this? Well, maybe the catalytic site needs to have this substrate bind here and this substrate bind here. Because you need the catalytic site to like open up, like the mouth of Pac-Man. It needs to open up. So those are the two binding spots. But then when that mouth closes, then they get aligned to react. Okay, and then that fourth and last one is basically what I've already been talking about. Just getting the molecules aligned so they can react. Okay? So those are the four things that you need to be aware of, okay, when reactions take place. And all this happens in the enzyme. It takes care of those things. Okay, I know you guys love mechanisms, and so we're going to do a lot of math and a lot of mechanisms here on out. So, recall from organic chemistry. I'll give you like 10 seconds to self-reflect here. Draw for me a reaction of a proton transfer. Could you do that? I hear people laughing. Proton transfers are the most simple and most basic mechanism, and they are prominent in biology. They're happening all over the place. So if we look at a very simple thing, we would have what? Water and a base. And how does that happen? We take the lone pair, grabs the proton, breaks the oxygen-hydrogen bond, and that's going to be a reversible process to give us hydroxide plus the new water molecule. Okay? That's what happens when you have water. That we have that equilibrium process, the KW. Okay, that's a proton transfer. We could maybe generalize it a little bit more. Like this, HA for an acid plus B minus for our base. And I can come, grab the proton to give us the conjugate base plus the conjugate acid, like that. Now in the catalytic site, we have catalytic sites for one reason. Well, there's lots of reasons, but another important reason is to get water out of the picture. We want to get rid of that solvent as much as we can. If there's too much water, then reactions just go AWOL. Why is that? Water is an acid and it's a base. So it can do these proton transfers just willy-nilly. We kind of want to limit that or have it in a controlled fashion. So the catalytic site doesn't have a lot of water. So how in the heck is it going to do a proton transfer in a catalytic site? And the answer is right there. The side chains of the amino acids in the catalytic site, those side chains are the things that are going to grab a proton or release a proton. So which amino acids are basic? Which amino acids are acidic? And so you have to relate those side chains to this general structure here. What side chains are acidic? What side chains are basic? And so in the catalytic site, there's going to be a lot of proton transfers happening. It's just not necessarily with water, because there's not a lot of it. But we have plenty of those side chains that can make that happen. And I'm laying the groundwork here because at the last bit of chapter 6, we are going to go through examples of enzymes. And I'm going to show you mechanisms. So we're going to always refer back to a proton transfer mechanism. Like, hey, you see over here, what has just happened? So we have proton transfers that can happen. Okay, let's see. Another thing that can happen is covalent catalysis. So we have, in an enzyme, we can have covalent bond formation. So let's consider a generic molecule. Okay? We have AB. And if we add water, we are going to do a hydrolysis reaction. And that's not how you spell it. This. Hydrolysis. What's going to happen when you take water to hydrolyze a bond? You're going to break them. You're going to use water to separate those two molecules. Okay? That's the definition of hydrolysis. But that's happening, that example that I just drew right there, is happening outside of an enzyme. That's where you have just this molecule, you throw some water at it, and it could break that bond. But what if we have an enzyme? Okay, and what do we have inside of enzymes? Well, we have the side chains of amino acids that can act as acids and bases. Okay? But I already talked about proton transfers. I'm here to talk about covalent bonds, covalent linkages that help catalysis or help the reaction. So we would have, I'm going to represent it by a X. Okay? And that X represents side chains of amino acids because side chains can now act as a nucleophile or a electrophile. And so if we act as a nucleophile, what can happen is this guy can come in and do this. AX plus B, like that. So that would have to be negative, like that. But then there's going to be a proton transfer that I'm not showing, okay? Or a transfer of electrons. Let's not worry too much about that. And then we would have another step here where we have a little bit of water. And then that can hydrolyze the bond to A plus X plus B, like that. Okay? So in the catalytic site, you can have covalent bonds that are formed with your substrate. And then we could use water to hydrolyze that as well. Now I want to mention this because it's in my notes here. This right there, that's a nucleophile. But where's that nucleophile typically going to come from? Typically it's going to come from a amino acid side chain. But we have cofactors and coenzymes that can bring in other functional groups, and there's a good possibility that it could be a non-amino acid, this nucleophile. But just be aware that, hey, we're going to form covalent bonds with nucleophiles. So if that's my nucleophile class in red, in green, what would I circle? Where's my electrophile for this reaction right here? Is it A, B? Yeah, A or B. What's our electrophile? Have to be A, right? Is that where the electrons are going? The lone pair came and attacked A. So that would have to be our electrophile. Okay, class, I am a little worried based off of your facial expressions that basic concepts from Orgo have left. We got to bring them back. Okay? And I'm not harping on you because they've left. I'm just making sure you're aware that I can see that they've left, and so you need to bring them back. Okay? And those people who are being honest with themselves and smiling and laughing already know they've left. So, got to get it back. Okay? Let's see here. So we have another type of mechanism in enzymes. Okay? And that is metal ions. Okay, so like when I talked about cofactors and all that jazz, those can bring in heavy metals like magnesium or zinc. And those metals can form, I wouldn't say covalent bonds, but coordinated bonds. Let's just say an interaction. Okay? So we have a interaction between the heavy metals. We have copper that's prominent in enzymes and things like that. So we have metal that promotes these mechanisms and these reactions. So I kind of just went through those briefly with you guys. So what are the three major types of mechanisms that you're going to encounter at the end of chapter 6? Proton transfers, okay? Covalent bond formations, and then what I just talked about right here, we're going to have some metals that are going to be present in the protein to help the reactions occur. And why do we care about all of those mechanisms? What is it doing? It's lowering the energy of activation to make this process happen at a faster rate. So why should you care about the mechanism? Why is that so important to study? Why is there so much research in it? Well, if you know the mechanism of how an enzyme works, then you can design inhibitors. You can design small molecules that will, if let's say there's a 5-step process for this enzyme, you'd be like, hey, at step 3 of the mechanism, that intermediate looks like an anhydride. Well, what if I design a small molecule anhydride that can interfere with that process? Let's say you want